All right, we finished up the solutions. Talking about solutions are when water or some other substance, some other phase like a liquid comes and then pulls apart another substance atom by atom and surrounds it. So salt, for instance, is a solid. When it goes into water, water pulls that apart. Water surrounds each atom and becomes a liquid phase. Salt, when it's dissolved, is considered liquid. We call it aqueous. Put AQ after it in a chemical reaction. So that was some things in solutions, and we talked about how to measure their concentrations. I'm going to talk about a particular kind of solution, and that comes from specific kinds of ionic compounds. And there are acids and bases. They're important biologically because they really govern. If you have too much acid or too much base, it will not, environmental systems and biological systems are very sensitive to acid changes. It also causes some pollution problems when we put so much CO2 and nitrous oxides in the air. They become acid rain. But they're critically important in driving chemical reactions in industry. So it's going to be an acid and base. Acid is just anything with an H in the front. HCl, HBr, HNO3. H with some other polyatomic ion or element. Bases are just something with OH in them. So sodium hydroxide, lithium hydroxide. What do they do? Acid's on a metal because hydrogen's in the middle of the single replacement series. There, it's one single element with HCl as a two-part element. H is in the middle. Metals are almost always higher and they kick H out, so it bubbles off. When you put acid on metal, it'll bubble off, the metal dissolves, and so that's what you see when somebody spills acid on the floor and they eats a hole through it. They're dissolving the metal, basically, and the hydrogen's coming off. They are ionic, so they conduct electricity. The H and the Cl, for instance, if they're in solution, are free to move, and they're minus and plus charge, so they can conduct. And they turn certain molecules colors, like litmus goes to red, phenolphthalein goes to red as well. So that's important just to know those two because they're the most common indicators. If you get them on your skin, they burn and leave blisters. If it's more dilute, and then it is more itchy, it's just irritating if you get lemon juice on a cut, for instance. And then it tastes sour if it's really dilute, and fruit juices have that taste. Whereas bases have OH on them, the metal that's with them to make them dissolve is usually a first column metal. Sodium hydroxide, lithium hydroxide are the ones in Drano. They are already high on the reactivity series, and something rarely kicks them off, and they don't react with metals. They do break down into plus and minus parts, so they are conductive. And the last one, they usually turn litmus blue, and phenolphthalein is going to be clear. Those colored molecules have a distinct color, and just knowing what they are is important. If you touch a base, a lot of times it'll feel slippery like soap. Bases help break down proteins and fats, so that will what they do, and your skin will get a sore on it because it'll break that membrane down if you don't wash it off in a hurry, so it still will cause damage. They do taste bitter, and so like dry wines and things like that are because they have a base like tannin compound in them. Now, I already said Arrhenius was the first to study acids and bases, and he just said anything with an H in it will add H to solutions, and that's why they are considered acids. He also said anything with an OH in it, sodium hydroxide, lithium hydroxide, is a base. Bronsted said, 10 years of using that was pretty good, but there was some reason to increase their understanding, and they said, hey, anything that can give up an H, it may not be HCl or something, but if it's got an H that can give into solution, that'd be great. Maybe because it steals something else that causes H to go into solution. If it can accept an H, pull an H onto it, it doesn't have to have an OH, but if it can pull an H onto it, it's a base. Lewis was the last scientist, and he gave a very ethereal sort of description. And in this level of chemistry, we don't need to understand that. So I'm not going to push that one, but it's there because it was in the notes. I want to talk about a term that is what happens if something can give up an H but also take an H. Just like if you're ambidextrous and two-handed, you can be amphiprotic, meaning water, which can give up an H as an acid, or it can pull an extra H onto it, and H2O becomes H3O. So that'll be amphiprotic. NH3 acts that way in any polyatomic ion that's got a more than a -2 charge. Because if you're a -2 and you lose one of the hydrogens, now you've got space for another hydrogen to come on, or you've got an extra hydrogen to give up. -2 or -3 charges have that capability. You should learn just which the strong acids are. There's really just 6 of them. Perchloric, or chlorate, nitrate, and sulfate. When hydrogen goes on them, we'll talk about the names in the next video. Hydrogen chloride, hydrogen bromide, hydrogen iodide. Those are in the second to last column. So if you know those 6, those are the strong acids. Anything else is a weak acid. It will give up the H grudgingly. There's also some strong bases. The first 2 columns in the periodic table, sodium or lithium or potassium, or the second column in the periodic table, beryllium, magnesium, calcium, all those hydroxides are bound to dissolve. They do dissolve. So that's what makes them strong. You should know at least by recognition an acid and a base that are weak. Acetic, that's acetate, acid, H with acetate is a polyatomic ion, C2H3O2. That's a weak acid, and NH3 is going to act like a weak base. It'll pull an H on, becoming NH4, which you already may notice and recognize from the polyatomic ion list. Now, when something is good at taking or giving up an acid, then you will just want to be familiar with the term called conjugate acid. If you have a reaction where something grabs an extra H, it's acting like a base, grabs the H onto it, then when it has the H, it's the conjugate to what it started as. So NH3 is the base, but its conjugate is when it has one more H. If it has one less H, then it's the conjugate base. So when water loses a hydrogen and becomes OH minus, its conjugate base to water is the thing with less H's, one less H. It's a conjugate base. So that's what a conjugate acid and conjugate base are.